Today we will analyze the response of an RC circuit when the input is unipolar current pulse train. Consider an RC circuit. Resistor is 1 kilo ohms, capacitor is 1 microfarad. Input current source is a square pulse with height equal to 5 milliampere. On time is 5 milliseconds, off time is 5 milliseconds. Since R and C are in series, the capacitor will charge and discharge accordingly. We will find out the voltage across capacitor, voltage across resistor, and the current flowing through the capacitor. Now this is the input current that we are feeding to the RC circuit. Between 0 to 5 milliseconds, the input current is constant 5 milliamps and the capacitor charges linearly, and the charging equation can be given as follows. Vc of t is equal to 1 by C integration I of t dt plus V initial. V initial here between the time period 0 to 5 milliseconds will be 0 because we have considered an uncharged capacitor here. On substituting the values of current, time, capacitor, we can find out that the voltage across capacitor at 5 milliseconds is equal to 25 volts. Now between 5 milliseconds to 10 milliseconds, the input is 0, hence current source is replaced by open. There is no path for the capacitor to discharge, hence the voltage remains at 25 volts. The voltage across resistor can be calculated by multiplying input current into resistor, and the current flowing through the circuit, since R and C are in series, same current will flow through the circuit and it is calculated by VR by R. Nature of charging is linear, as we can see here in the graph. The nature of charging of the capacitor's voltage is linear. Now from 10 milliseconds to 15 milliseconds, again input current of 5 milliampere is available and the capacitor now charges linearly to 50 volts with 25 volts being the initial value, and from 15 milliseconds to 20 milliseconds the input current is 0 and the current source is open, hence voltage across capacitor remains at 50 volts and adds up when the input current appears in the next cycle. The voltage across resistor can be calculated using this equation, input current into resistor, and the current flowing through the circuit can be calculated as follows. Here we have calculated directly at 15 milliseconds and at 20 milliseconds. At 15 milliseconds the voltage is 50 volts and at 20 milliseconds the voltage is 50 volts. Let's consider different time steps between this on time and look how the voltage across capacitor builds up to 50 volts. Now to capture precise charging profile of Vc and voltage across resistor and current flowing through the circuit, the calculation is repeated in Excel with more finer time intervals of 20 microseconds. Let's look at that. This is the input that we are feeding to the RC circuit. On time is equal to off time is equal to 5 milliseconds. Voltage across capacitor, voltage across resistor and current flowing through the circuit is calculated every 200 microseconds. Now on plotting it, we can see how input current has transformed the voltage across the capacitor, the voltage across the resistor and the current flowing through the circuit. The voltage across the capacitor can be calculated using the same equation, I into T by C plus V initial. And similarly, voltage across resistor is input current into resistor. Current flowing through the circuit is VR by R. The current flowing through the circuit and VR by R looks similar because this current flowing through the circuit is calculated using VR. By dividing this by resistor, we are getting current flowing through the circuit. Let's consider the case where T on is much greater than T off. T on is 7 milliseconds. This is the input that we are feeding. T off is 3 milliseconds. Let's look at how the voltage across capacitor, voltage across resistor and current flowing through the circuit varies when T on is much greater than T off. Now the voltage across capacitor is 35 volts. And when the input is 0, it remains at 35 volts. Let's consider one more cycle. Between 10 milliseconds to 17 milliseconds, it has charged up to 70 volts, and between 17 milliseconds to 20 milliseconds, the input is 0, hence replaced by open, and it remains at 70 volts. And it remains at 70 volts and adds up when the input current appears in the next cycle. VR by R looks like this, and the current flowing through the circuit looks similar to VR. Now here the on time is 7 milliseconds, off time is 3 milliseconds. This is the input current that we are feeding. Now the voltage across capacitor has charged up to 35 volts at 7 milliseconds and it has charged up to 70 volts at 17 milliseconds. This is the voltage across the resistor. This is the current flowing through the circuit. Let's consider the case where T on is much lesser than T off. T on is 4 milliseconds, T off is 6 milliseconds. This is the input current that we are feeding. The voltage across capacitor between 0 to 4 milliseconds can be calculated using this equation. At 4 milliseconds, the voltage across capacitor is 20 volts. And at 10 milliseconds, it remains at 20 volts because there is no path for the capacitor to discharge. And this is how the voltage across capacitor looks like. Now let's consider the case where T on is much lesser than T off. T on is 4 milliseconds and the voltage across capacitor at 4 milliseconds is 20 volts, is calculated to be 20 volts. And T off is 6 milliseconds. Now at 10 milliseconds, the voltage across capacitor still remains at 20 volts because there is no path for the capacitor to discharge. This is how the graph looks like. Voltage across capacitor is charged up to 20 volts and it remains at 20 volts until 10 milliseconds. Now for the second cycle, at 14 milliseconds, the voltage across capacitor is charged to 40 volts. And at 20 milliseconds, it remains at 40 and adds up when the input current appears in the next cycle. This is how the voltage across resistor looks like. And this is how the current flowing through the circuit looks like. Here on time is 4 milliseconds, off time is 6 milliseconds. This is the input current that we are feeding. The voltage across capacitor is calculated using the same equation, I into T by C plus initial voltage. And this is how the voltage across capacitor looks like. And this is the voltage across resistor, which is equal to I in into R. This is how the voltage across resistor looks like. And this is the current flowing through the circuit, which is equal to VR by R. Let's simulate this and check. Let's simulate for the case where T on is equal to T off is equal to 5 milliseconds. On simulating this, we can see that this is the input current, which is equal to 5 milliamps. The voltage across resistor has charged up to 25 volts during the first on period from 0 to 5 milliseconds, and it remains the same until 10 milliseconds. This is the voltage across the resistor. This is the current flowing through the circuit. Here is the summary for the case where T on is equal to T off. This is the input that we are feeding, and this is how the voltage across capacitor, resistor and the current flowing through the circuit looks like for the input fed to the RC circuit. If the time constant of the RC circuit is comparable to the input pulse width, then it will not resemble the behavior for unipolar current pulse train input. Thank you for watching this video.